Oh, I see. So let's start. Hi everyone. This is the first lecture on categorical K theory in the K theory and totality series. Today's professor, uh, oh yeah, today's speaker is Professor Sarang from IIT Madras. He's going to talk about the K theory of monoidal categories today. He'll also deliver another lecture on the K theory of abelian categories next week. So yeah, let's start. Over to you, Professor.
Yeah, thank you, Dipankar. Yeah, I should first thank Dipankar for his enthusiasm in conducting the series. And I think I also, I mean, I'm not really in any sense uh, an expert at the topic at hand. I think I'm not quite the, I mean, there are many things I'm not quite competent enough to speak about. But anyway, I also got sort of carried away by his enthusiasm, and hence I'm here. Uh, so I'll say that yeah, I there are things that I plan to do, but I'm not sure I both in terms of time and in terms of how much I have understood them, I'll be able to get there. So till a point, I think I'll go, and then we'll see how it goes. Okay, so let me first recall what has been done before. So this is yeah. Also, at any point, if you feel like there is something that you want to comment, please stop me right there. And I hope everything is visible. If there is any like technical issues, please let me know. Okay, so with that, let's get started. So I today I'm going to talk about essentially the S inverse S construction. S is going to be a symmetric monoidal category, and then uh, we heard about two constructions in the last few talks: the plus construction and the Q construction. And today is about the S inverse S construction. And well, depending on how far we get and etc., we'll try to um, put the all three together in some way. But I'm not sure I'll get that far, and also whether I have understood enough to clearly say it. Okay, but let's start from the start. So let's recall the previous talks in this series. So uh, initially K0, K1, K2, these were defined, I think, by the first speaker, Professor Amit Kuber. And then after that, Professor Girja Shankar Tripathi, he defined the higher kns for a ring R. And all of these were defined using the category of finitely generated projective R modules. So, so one of the things that one noticed when doing this, and this was emphasized also by the first speaker, was that the isomorphism classes there in this category, they formed a commutative monoid under the direct sum. And then the way K0 was obtained was by group completion. So this was a monoid, and then one can look at the Grothendieck group of this monoid, and that was the definition of K0. And then later on there were definitions of K1 and K2, probably due to Bass, and they were defined using automorphisms or GL. Okay. So the next thing that, so this was more or less what, and then there was a long exact sequence connecting these, and one had to define relative K groups, etc. So with that, one got a long exact sequence, and that was the first part of the course. So the next thing that was done was that the higher kns were defined, and in order to define them, so Professor Girja introduced the classifying space for a group G and for a category C. And then he briefly described the plus construction, which was if you have some normal subgroup of G, then you look at this classifying space BG, and then you attach certain cells, and then you create a new space, and then you take the homotopy groups of that. That was how higher kns were defined. Okay, with some small caveat, namely that k naught was not recovered from this, so you sort of artificially put in k naught, right? So this was the plus construction, and then finally he defined rather briefly. He said you can, for the category of projective module, or more generally what is called an exact category, you can create a new category called the Q, and then take the classifying space for that. So and then look at its homotopy groups after taking, I think, loop space. Yeah, so this is summarized in that last point there. So Kn of R was defined either as pi n of K naught R cross BGL R plus, where that K naught R should be thought of as a discrete set, or in terms of the Q construction. So I think this is broadly a summary of what has happened before. Okay, so let me sort of sketch out what originally my plan was for this talk. But as I wrote down more and more, I felt I'm not sure how far I can go. So we'll just recall first PC and the classifying space, and we'll prove or at least state some relevant lemmas. Then we'll define monoidal categories. We'll describe the S inverse S construction. So this is sort of the main goal of this talk. So I think I can get that far for sure. And then define the K theory. So this we have to do. And then the last few things are really topological gadgets in order to connect um, the other things, all these constructions, the plus construction, the Q construction, and the S inverse S construction. So I don't know if I have enough time to do that, but at least I may say a few words about 5 and 6, and then 7. I don't know if I can get that far. We'll see. Okay, so this is the plan for the talk. Okay, so let's start with the classifying space. So for a category C, the first thing that was done was one associated simplicial set to this category. So this was called the nerve of C, and yeah, so this was like NC, the notation. And so a simplicial set consists of the following data. For every n, you have to specify a set, and then for morphisms from m to n, meaning 0, 1 to m up to uh, you take the set 0 to m and then 0 to n integers, and then you take maps which are increasing, meaning order preserving, rather, not increasing. Right word is order preserving. Right. So given such a map, you have to associate corresponding maps from NCN to NCM. So let's recall how to do that. So the set corresponding to N, so this was where you took objects from this category. So all these AIs are objects, and then you put morphisms between them. So F1 is a morphism from A0 to A1, F2 from A1 to A2, and so on up till Fn. So any such chain is an element of NCN. So all such chains together give you the set NCN. And now if you have a morphism from M to N, so remember that these are order preserving morphisms. So that means if you have two integers I and j between 0 and m and I is less than j, then image of I, so alpha of I must be also less than equal to alpha of j. Okay, so by order preserving, one doesn't mean strictly order preserving, but only up to less than equal to. Fine. So fine. So once you have an alpha like that, you want to associate a map from the set NCN to NCM. So how do we do that? So if you have a chain A naught through AN, uh, it should go to some other chain of length M. So what is that chain? And what are first of all the objects, right, in that chain? So we'll define Bj to be A alpha j. And then, so if you have A0, A1, so many of these integers from between 0 and n could go to the same integer, right? That's possible. So, so if you want the, say I want B3, then I guess you should take like, no, there seems to be, oh, my bad. Right. So this is a contravariant functor, right? So so I have morphisms from M to N, and that should give me a maps from NCN to NCM, right? So I have an N chain, and I should associate an M chain to that. So if you want Bj, you look at A alpha j. So j is between 0 and m, and then alpha of j is some integer between 0 and n, and you look at that corresponding object. So that's Bj. So this makes sense, right? And yeah, notice that if j is, I mean, if you take j and j plus 1, then Bj is A alpha j, and Bj plus 1 is A alpha j plus 1, and alpha j is less than or equal to alpha j plus 1. So from A alpha j to A alpha j plus 1, there are two possible ways of defining maps. If alpha j is strictly less than alpha j plus 1, then you look at all the composite maps in the middle, then that's your Gj. And if it's equal, then you put the identity map. So this is the uh, definition of the GIs. Yeah, the definition of the GIs here. Right. So I hope this is okay. So just as an example, let's write down what happens for face maps and degeneracy maps. So if you have, let's say, A naught through AN, then this should go to, so this skips J. So you should have, let's see, so this is, so I need n plus 1 here, not n, right? And then this skips j, so I should have something of length n. So a naught through a j minus 1, and then aj plus 1, and then an. And this is the composition of aj minus 1 to aj and aj to aj plus 1, right? That's what will happen for the face maps. And for the degeneracy maps, you will get, you have an. So I hope this is visible. Let me know if there's any. So here we'll start, okay, you start with an minus 1. And then when you reach the ith place, you repeat ai. And then you go on. An minus 1. Ah, this should have been an plus 1. Right. So this is what will happen for the phase and degeneracy maps. Okay. And I think this was kind of, for small examples, this was small numbers. This was mentioned in Professor Girja Shankar Tripathi's talk. Okay. So I hope this part is okay. Maybe you have seen this already before in other series as well. Hello. Any question? Yeah. Okay. So so now given this category, we got the simplicial set, which is called the nerve of this category. And now you take its geometric realization. So that means out of this, you create a simplicial or CW complex by taking, for the set corresponding to n, you take that set cross the nth simplex, take a disjoint union of those, and then go modulo the attaching maps given by uh, coming out of degeneracy and face maps. Okay, so this is the construction. So let me describe a few properties. So if you have a functor f from between two categories, yeah, and I should say, of course, this all makes sense for small categories. So wherever it's required, please assume that the category is small. Otherwise, one has to keep making hypotheses. Okay, so if you have a functor of small categories, then you get a continuous. In fact, this is a CW or simplicial map from the classifying space of C to the classifying space of D. That's because from C to D, once you have a functor, you get a map at the level of nerves of simplicial sets. And then once you have a map of simplicial sets, that converts to a map of a continuous map from BC to BD. Okay, so there's a special category that is very important to what's happening. Again, I think this was mentioned in Professor Girja's talk. So if you have the category C and it has two objects, namely the objects 0 and 1, and it has three morphisms: the identity morphism for 0, identity morphism for 1, and one extra morphism, namely a morphism from 0 to 1. Right. So then if you construct the classifying space of this category, this will exactly be the unit interval 0, 1. So I think this is fairly clear because the corresponding simplicial set will have, I mean, the non-trivial sets will be 0 at level 0 and level 1, which will consist of 2 points, namely the vertices in at level 0 and um, 1 point in level 1. And then when you, as a result, when you go to the realization, that will give you just the interval or an edge with two vertices. Okay, so this category we'll denote by this notation, 0 going to 1. Okay, so next, there's some slightly technical sort of topological details that we have to work through here. So if you you can look at the functors C cross C prime to C and C cross C prime to C prime, right? You can first of all construct the product of categories. If these two are small, then the product is also small. And then you can look at what one would think of as projections, right? So because functors induce continuous maps, you will get continuous maps from the product category to both of these projections. So BC cross C prime to BC and BC cross C prime to BC prime. And then based on this, you will get a continuous map from B C cross C prime to B C cross BC prime, at least as topological spaces. And CW, you have to be a little careful when you take products, but yeah, at least as topological spaces. Okay, so now notice that the objects of C cross C prime are the same as the objects of C cross objects of C prime. And similarly for morphisms, they're just products again, the morphism sets. And because of that, uh, the um, uh, the map here that you get is a bijection. So I hope this is okay. So this map is a bijection. This map, by this map, I mean this map. BC cross C prime to BC cross BC prime. Okay, so it's a continuous bijection, but it's not clear that this is a homeomorphism. I mean, that's what you would expect and want, but unfortunately, that's not clear that it is. So it depends on what kind of topology you have. So there is a condition which if that is satisfied, then it is a homeomorphism, and the condition is that if the right hand side is compactly generated. So if the right hand side is compactly generated, then this does give a homeomorphism. Okay, so what is compactly generated? Just to recall, so one way of thinking of compactly generated is that this is built out of things at well, okay, so it has compact sets. You look at all compact sets, and if you can say that a set is open, I mean, this is not the definition, but it matches with the definition in most good cases. So if a set is open, if and only if its intersection with every compact set is open. So one way is, of course, fine. The other way is not so clear. I mean, it is not clear. So that's when it's called compactly generated. So if that happens, then it's called compactly generated. So I'll just repeat. If a set is open, if and only if it's open when intersected with compact sets, then it's called compactly generated. So if that property, if the right hand side has that property, then this turns out to be a homeomorphism. And it's a fact that if either of these is locally compact, then the right hand side is compactly generated. Okay, so the upshot is that if one of these components, the classifying space of C or the classifying space of C prime, is compactly generated, then the map, then the functor taking products, then the classifying space functor respects products. Okay, so this is the upshot of what we are doing, and this is one reason why often people prefer working in the category of compactly generated spaces, because of issues like this. Okay, so now we really want to do this only in some very special categories. So I'll straight away say where I want to use this. So if you take this product C cross 0, 1, right? So if you take 0, 1, then if you take its classifying space, we saw that's the interval, and of course the interval is compact, so no issues. I mean, so certainly it's locally compact, and because of that we can apply that previous result and say that the classifying space of the product of these is indeed the classifying space of C cross with the classifying space of 0, 1, which is meaning the category 0, 1, which is the interval 0, 1. Okay. So the upshot is that the classifying space of this category C cross 0, 1 is the classifying space of C cross 0, 1. Now this suggests that some homotopy, we want to do something with homotopies, right? Because that's where you see this interval playing a role. And indeed, that's what is next. So if you have two functors, f and g from C to D, we saw that functors induce continuous maps. So this will give you continuous maps from BC to BD. And we want to compare these functors in case, I mean, these maps in case the functors themselves can be compared in some way. So suppose there's a natural transformation f to g, and let's denote that by eta. So now note that the data of a natural transformation is exactly same as the data of a functor from the category C cross 0, 1 to D. So just to make this clear. So I want to construct a functor like this. So to do that, I should tell you what happens for a comma 0. Where does this object go? Where does a comma 1 go? And then we have to look at the maps. So I should tell you where a map of the form f comma identity 0 goes. I should tell you where a map of the form f comma identity 1 goes, and I should tell you where a map of the form f comma 0, 1 goes. Right? This is if I can do all of this, then this is what will construct a functor. So a comma 0 will go to f of a comma 1 will go to g of a, and then f comma identity of 0 will go to f of f comma identity 1 will go to g of f, and what's remaining which we haven't used yet is the natural transformation. So when you have f with that extra arrow 0 to 1, so this should go to the following. So here, so I'll put this over here. So you have, so suppose this f is from objects A to B, right? F is from A to B. So then you have f of A to f of B, f of f, and you have g of A to g of B, g of f, and now you have this natural transformation. So that gives you eta A and eta B, and this diagram commutes. That's what you know. So really there's no choice. You send this f comma 0, 1 to let's say eta B composed f of f. And let's see if this goes from the right place to the right place, because this takes f of A to g of B. So this map is from where to where? This map is from A comma 0 to, sorry, it's not maps to, just a map. So A comma 0 to B comma 1. So indeed it should go to, this should be a map from f of A, which is the image of A comma 0, to g of B, which is the image of B comma 1. Right. So indeed that's the map eta B composed f of f. And now this put together will give you, you can now, I mean, there's a few other things you have to check, composition, etc., identities, so that you can check. Okay. So this data C cross 0, 1, this, I mean, this oops, excuse me. The data of a natural transformation is exactly the data of a functor like this. Okay. So now, because of that, we get a map of classifying spaces. So we get a map from BC cross this category 01 to BD, which is a continuous map. But we just saw in the previous one of the previous points, because 01 is compact, meaning its classifying space is compact, we can write this as BC cross 01 to BD, right? And what happens at BC cross 0? So you can check that that's exactly the map BF. And what happens at BC cross 1? You can check, meaning when you restrict to BC cross 1, you can check that's exactly the map BG. So that's an easy check based on our definitions here. So I'll encourage you to make that check. And so what you get is a homotopy from BF to BG, right? So this is a homotopy from BF to BG. Okay, so the upshot of this is that if you have a natural transformation from between two functors f and g, then the induced maps on the classifying spaces are homotopic. So now note here what happened. On the left side, you have just a natural transformation. It's not a natural isomorphism. It's just a natural transformation. But on the right side, you have some things which are homotopic. So you can really, I mean, if BF is homotopic to BG, you can flip that around, right? So the right hand thing is something symmetric, but the left hand thing, you just have a natural transformation. And this is very important for what's going to happen later, because often what will happen is that we'll have functors and it will seem like there is some relation between them, but they don't really seem uh, 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 like they won't seem to have a natural isomorphism between them. But when you go to the level of classifying spaces, just having a natural transformation will say that somehow they'll produce homotopic maps, and that will give us good properties for whatever we want to do. Okay. Okay. So just as an example, which is the example that I have here. So if F has a left or right adjoint, then BF is a homotopy equivalence, right? So let's quickly go through this proof. So if F has a, let's say F has a right adjoint, right? That means you have another functor G, and so there is what is called a unit of adjunction and a co-unit of adjunction. So that means you get, so the unit of adjunction will give you, so those two will give you natural homomorphisms, say epsilon and eta, from F compose G to identity of D. So let's say, yeah, I didn't write. So G is from, F is from C to D, and G is in the reverse direction, right? So if you do F compose G, that's a functor from D to D, and being an adjoint pair will imply that there is a natural transformation to the identity of D, the identity functor on D. And you also have a functor natural transformation from the identity functor on C to GF. So what does that give you? That gives you that if you take BF composed BG, that's homotopic to identity of BD. And if you take BG composed BF, that's homotopic to identity of, this is a mistake. This should be BC. So just having adjoints produces homotopy equivalences. So this is what I meant when I said uh, the relation on the functor side is not symmetric, but the relation when you go to homotopy somehow turns out to be symmetric, and it gives you this very nice um, these nice kinds of results. Okay, so one immediate corollary of this is that if you have an initial or a terminal object in your category C, then uh, then the classifying space is contractible. So why is that? So that's because if you have you take the category with one object and just the identity morphism, and uh, so let's call it star, and so you have these two functors. So the functor C to star, there's no option. You send every object to star and every morphism to the identity of star. The functor star to C, so that you have a choice. You can send star to some object and the identity on star to the identity of that object. Now, if okay, or so now if so one of the equivalent formulations for an object to be an initial object is that uh, it's part of an adjoint pair like this. I forget which one is left and which one is right. And similarly for it to be terminal, it's the opposite pair. Okay, that's an if and only if condition. So once you have that, these will induce homotopy equivalences. But then you know that for the singleton category that we have here, the classifying space is just a singleton point, and from there you get that it's contractible. Okay, so this is the corollary we will need in the next talk that I'll give. Okay, so that's all I wanted to say about classifying spaces. Maybe some of this was already done in previous things. If there are any questions, please go ahead and ask me. Okay, so let's go on to monoidal categories. So, well, being categories, of course, there's no option but to have lots of huge diagrams, and so this part will have lots of big diagrams. So I'll try to sort of go through it rather quickly because I mean there's not much. It doesn't really serve a lot of purpose to check every detail in those diagrams, but I'll give you an idea of what they mean. Okay, so so I can see a typo. Let me correct that, please, first. Right. So this is the generalization of monoids. So I think you already saw this again in Professor Amit Kuber's talks, where he sort of sketched what this was. But this is like the formal definition of the same thing. So the idea is to generalize monoids. So here's the data that you need. Hello?
Sir, I have a question.
Yeah, sure.
So when the small categories are taken to be GLs, so for that, will it be always locally compact? BGLs are locally compact?
I don't know actually. That's a good question. Locally compact they should be, I guess. Yeah, how do I? Yeah, I guess. So okay. So BGL is like the union of the limit of BGLN.
Yes.
And hello.
Yes, sir.
Yeah. So BGLN we know explicitly. We have a model for BGLN. Namely, it's the what is it called? The Grassmannian, right?
Okay.
It's there's something called the Grassmannian. It's like the projective, uh, like some generalization of the projective space. So instead of instead of taking lines, you take all planes,
Mm-hmm.
and then you kind of identify them in some manner, right? So that's the model, and yeah, that is well known to be like it's a smooth manifold, etc. So certainly it's locally compact, and since this is direct limit, this will also be locally compact. Yeah, so I think locally compact should be fine. Yeah.
Thank you.
Yeah, thanks. Oops, sorry. Okay, so coming back to symmetric monoidal or monoidal categories. Here's the data that you need in order to define them. I'm sorry that this is a lot of words, but anyway, we'll go through it once and hopefully won't bother about it later. So what does this involve? It involves a category S, a functor S cross S to S, which we have denoted by the tensor product, but depending on the context, it may be something else. So these are also called tensor categories, which is why it's denoted by the tensor product. So that there are different names for the same definition. So I'll go with monoidal since that's the standard name in this K theory world. Okay, so so there's a functor from S cross S to S. There's an object called 1, and it will act like 1 under this tensor, meaning when you take an object and tensor it with 1, it should give you back that same object. But of course, we have to make that more precise, etc. Then there's a natural isomorphism, which I'm calling alpha. So this alpha is in place of A, and that A is the associativity axiom. So what does this natural isomorphism do? It takes X tensor Y, then you tensor that with Z, and on the other side you have X tensor, Y tensor Z, and it's an isomorphism from the left one to the right one. So this thing here. So we have this for all objects X, Y, Z. Then you have a natural isomorphism lambda. So the lambda is for in place of L, where this L is where you so I forget what this is called, the left uniter or something, this isomorphism. So where basically you take one on the left and then you say that one tensor X is isomorphic to X, and in a sort of natural way, so that hence a natural isomorphism. And similarly you have rho, where rho is for R, and where now you have one on the right, and this is a natural isomorphism again. And then of course you have to sort of put all of these together and make certain diagrams commute. So the idea is that you want the you basically want to get rid of brackets, right? So you can just do everything without brackets. Of course, there'll be some isomorphisms floating around, but modulo those some isomorphisms which are natural, you can just get rid of the brackets. This is the idea. And then whenever you have tensor with 1, you can just knock that tensor with 1 off. Yeah. So these diagrams are meant in order to do that. Okay. So here is the first diagram. So if you have X tensor 1 tensor Y, and then X tensor 1 tensor Y, then there is a natural map between the two. Let's put that in. Let's try to give these maps so that we keep track of what's going on. So this was I think we called this eta X comma 1 comma Y. Not eta, sorry, my bad. Alpha X comma 1 comma Y, right? And then you have X tensor 1 tensor Y. So this is so extensor 1 to x, you have the right so row x, and then this is just tensor with y. So it's a natural thing. So you have, this makes sense, row x tensor y. Meaning S tensor S to S, S cross S to S is a functor. So from there you have something like this. And similarly here you have X tensor. So now you have one on the left. So you have lambda, right? Lambda y. Okay, let me just check that was what we had. Right, so we had lambda and rho. Okay, so this is what we had, and these diagrams should commute. And this is okay. Rows were also isomorphisms. This was also isomorphism. Yeah. So this diagram should commute. Yeah. So this is what you need. This of course happens for all objects x and y. And this is a rather nasty. So this is called the triangle axiom. This is called the triangle axiom or triangle property or something. And this is called the pentagonal axiom. Or pentagonal diagram, whatever. Okay, so what is this diagram? Again, let's put in the maps so that we can, otherwise this won't make sense. Okay, so it starts from here. So let's start from here and go this way. So we'll go this way, and then we'll go this way. So first let's go this way. Okay, so what is x tensor y? So what is this? This is oof. So this is eta x tensor y comma z comma w. So that is this map isomorphism.
You mean alpha?
Oh, thank you. I am bad. Yeah, I don't know why I'm stuck on eta. Okay. Thank you. Right. And then the one here is, let's see. So Z tensor W is the same. And then, so here you have, I guess, alpha X comma Y comma Z tensor W. So that those are these two maps. And then this side, let's do that. So this is alpha. So you have, so this is something tensored with W. So that's constant. So here you have just, I think, alpha X, Y, Z. So alpha X, Y, Z tensored with W. And then this isomorphism is where now you just shift the brackets. So this is alpha X comma Y tensor Z comma W. And then this isomorphism is where you have X tensor alpha Y comma Z comma W. Okay, fine. So this happens for all objects X comma Y comma Z comma W in the objects of S. So as I said, this is not something we want to, I mean, we don't want to keep using this, but if you want to really be careful and do everything, you have to use these in order to, manipulate the brackets. That's the main point. Okay, so these are the kind of things you have to do once and then forget for life. So I thought I would present it once because I don't know if this was done before. Okay, yeah, so the remark here is that these conditions are meant to ensure that all natural identities one can think of are true. So for example, you can think of lambda 1, which is where you multiply 1 on the left to 1. This is an isomorphism. And then you can think of rho 1, which is where you can multiply 1 on the right with 1. Okay, this is an isomorphism. Okay, so exercise is to check that, yeah, they're actually equal. No, I mean, these are not particularly hard, but you have to get your hands dirty. Otherwise, it won't make sense. Okay, so those are the axioms. So as we go ahead, let me point out that as we go ahead, see these axioms here, the three axioms at the end, not axioms, the part of the definition, alpha, lambda, and rho. Often these are dropped. Even the one is dropped in the context, because usually when you have like specific categories, these four are kind of clear once you know what the operation is. So the only thing that can change, sometimes you may have different operations on the same category. But once you have an operation, the other things are typically clear from what the operation is. So the point I'm trying to make is, as I go ahead, I may just write S along with tensor. In fact, I may even drop tensor when it's clear what operation I'm using. Okay, and that's okay. Like in the context that will come, it will be clear what I'm doing. Okay, so I think yeah. Okay, so once I have a symmetric, oh, I didn't say symmetric. Once I have a monoidal category, I can ask for functors between such. Again, this should be sort of the natural definition, but let's go over it once. So actually, there are two or three different definitions, and it's kind of important to know which is what. Okay, so a functor, sorry, yeah. So a functor is the following data. So there'll be, it's a triple f, epsilon, and mu, like this, and between two such monoidal categories. So this is called a lax functor if it has the following properties. So first of all, you just think of S and S prime as categories. So F should be a functor between these categories. The epsilon should be a, so now if you look at f of 1, right, there is an object 1 in the objects of S. So you have f of 1, which is an object in S prime. So you expect that there is some relation between 1 prime and f of 1. Now, for a lax functor, you only assume that there is a morphism from 1 prime to f of 1. Okay, so that's what this epsilon is. Okay, there are stricter definitions of functors, and they will assume more properties, but for a lax functor, this is just a morphism. Okay, then you have the third thing was you have a natural transformation, which is mu. Okay, so what does mu do? So in the first two, the operation didn't come into play at all. So there has to be some relation between the operation tensor prime and tensor. So what it does is it says there is a natural transformation, and again, it's only saying transformation and not isomorphism. Between, you first take f and then take the operation. So that's f of x tensor prime with f of y. And on the other side, you have f of, you first do the operation and then take f. So f of x tensor y. And there should be a map between these, which is natural with respect to x and y. Okay, and then you have some further diagrams, and yeah, such is life. So there are some diagrams which commute. So what I'll do is I'll skip this, because I think, this is not going to add to anything, but I'll recommend that you please go back and sort of read this on your own. So there are certain diagrams which you naturally expect to commute, and that's the demand that they do. Okay, so you can move your tensors around, you can move your brackets around. That's more or less what it does. And similarly for the 1 and 1 prime, right? You can tensor with 1 prime, or you can first tensor with 1 and then take f, etc. They should have some relation, and indeed those are the diagrams here. Okay, so if you're agreeable, I'll just skip this part, because I realize it's 3:59. I should get, we are still a little way off from where we want to be. Okay, so that's a lax functor of monoidal categories. Now in this definition, if epsilon is an isomorphism and mu is a natural isomorphism, yeah, which is very often the case you will have when you use this, then it's called a strong monoidal functor, right? It's a, so sometimes the previous thing which I called a lax monoidal functor is also called a weak monoidal functor. So this is called a strong monoidal functor, or sometimes you just drop the strong and call it just a monoidal functor. So if someone says this is a monoidal functor, then it means yeah, these are isomorphisms and natural isomorphisms. And sometimes you have even stronger assumptions, and in a couple of places later we will have reason to use those. Namely, if epsilon is actually the identity, which means that uh, f of 1 is actually equal to 1 prime, right? And similarly, mu is not just a natural isomorphism, but actually the identity uh, uh, between those two. So mu is also, meaning when I say mu xy is identity, so then it's called a strict monoidal functor. Then it is called a strict monoidal functor. And this is actually, I mean, this may seem like hair splitting, but this is actually quite important, like these three classes of functors. Okay, so with that, one final thing, namely so when, I've been sort of flitting between saying monoidal and strict symmetric monoidal categories. So I have to define when it's symmetric as well. So if the monoidal category has this extra natural isomorphism from X tensor Y to Y tensor X, and again some diagrams have to commute. So I've drawn all of those diagrams. Then it's called a symmetric monoidal category. So there are other words for this. Sometimes it's called, this R is called because they come from other places. It's called an R matrix, or it's called braided, etc. So all of that is code language for symmetric monoidal category. Okay, so symmetric just means X tensor Y is up to isomorphism, natural isomorphism, same as Y tensor X. So now, if you are in a symmetric monoidal category, you can do your tensors without bothering too much about like the brackets. You can flip things around with tensor, and whenever you have a 1 appearing in the objects which are being tensored, you can just drop it. Okay, so this is basically what we want. This is the data of a symmetric monoidal category. Okay, so here's lots of examples. So some of them you already saw in Professor Kuber's lectures. So this is finite sets with disjoint union, and the empty set playing the role of the unit. Then the next one also you saw, which was finite dimensional vector spaces with direct sum and 0. And as I said, I'm not writing down the other things because in these cases, it's clear what they are. Okay, then of course you can do a little better, and you can take modules over a ring with direct sum and 0. And if your ring is commutative, then you can do the same thing, and you can take the actual tensors, right? You can take tensors, and then R is the unit in that case. Okay, so yeah, so I should point out that well, okay, let me say, yeah, let me point it out a little later. So if you have a monoid, so which is a set along with a product and a which is associative, etc., and a unit for that product. Then you can look at the corresponding category, the you can look at the discrete category, which is you take its objects to be the elements of M, and you take tensor to be the dot, and you take 1 to be this unit 1, right? Then this will give you a symmetric monoidal category. So every monoid will give you a symmetric. Okay. I didn't assume it was a commutative monoid. So every monoid will give you a monoidal category. If it's a commutative monoid, it will give you a symmetric monoidal category. So the rest of the things one has to check, but it's more or less the same because monoids already have associativity, etc., built into them. Okay. Then, the important examples going ahead, projective modules, direct sum and zero. We have already seen this. Well, be a little bit careful. Finitely generated projective modules, direct sum and zero. This category you've already encountered. This was what was the building block for K-theory. Vector bundles, again, finite rank over a topological space X. And so if you know what is a vector bundle, I'm sure you know how to take sums of them. So there is such a notion, and under that it forms a monoid. And so you can form the corresponding symmetric monoidal category. Okay, its isomorphism classes form a monoid. By itself, it forms a symmetric monoidal category. And then sheaves, or some smaller collection, namely locally free sheaves. So you will encounter these as you go ahead. Fine. Then a couple of other ones, just to sort of because all of these may seem like, okay, really there's an underlying monoid that's doing everything. But a couple of other examples which are built from other kinds of data. So if you have a category, then you can look at all the functors between from that category to itself. And if you take composition, then that's a symmetric monoidal category, not symmetric. It's a monoidal category. So it's not symmetric. Yeah, this category is not symmetric. Okay, here's another sort of obvious construction. Namely, you take if you have a monoidal category, you just define the tensor on that, the operation on that by the reverse way. So you reverse the operation, and that gives you with some, to be careful, and that will give you a new monoidal category. And then there's two more examples. One is where you take the category of finite sequences of objects from C, and then you define morphisms between them only if they have the sequences of the same length, and in that case it's just the Hom sets, product of the Hom sets, it's zero otherwise. And then you can define the tensor by concatenation, and you can check that this is a monoidal category, again not symmetric. And finally, you can take a commutative ring, and you can take the category of bounded chain complexes of this ring, and then there is an operation on this chain complexes. Namely, if you take two complexes, you can form the double complex by tensor, the tensor double complex, and then you can take its total complex, right? So if you do that, then that gives you another bounded chain complex, and this operation satisfies all the properties of being or makes it a monoidal category. Okay, so this is checking. It has to do this checking, and this last thing I think you may see later on, again depending on what approach the person who teaches Waldhausen K-theory takes. Okay, so lots of examples. Maybe good idea to check some of them. Okay, so the last thing in this section that I want to do, it's 4:10. Okay, should go fast. Is talk about cofinality. So we have already seen cofinality in Professor Amit Kuber's talk. So that was when you had a monoid and you had a submonoid of that. And if you have an element in the bigger monoid, then you can um, take the operation with respect with some other element and bring it into this smaller monoid. Then that's when this was called cofinal. It's the same definition here, more or less. So if T is a full subcategory of S, and you have that the operation respects, meaning it descends to T, so it restricts to T, and that 1 is in the objects of T, then T is also a monoidal category, first of all, because all the other things were just, associativity, etc. They just design directly. Those diagrams work out. So then the natural inclusion is a strict monoidal functor. So in this case, it's a strict monoidal functor because, you actually have identities. It's the same one. It's the same equalities, etc. So then T is said to be cofinal in S if whenever you have S in the objects of S, there exists S prime in the objects of S, such that when you tensor the two, that becomes an object of T. Yeah, so the same definition that you had for monoids, and we will have a theorem later on that will connect the K theory of S and T, and I suspect we are not going to get that far, but let's see. Okay, so I think in the next 20 minutes, I think we have enough time to describe the S inverse S construction. Okay, so yeah, so this is the key sort of thing in this talk. So the idea is that if you have a symmetric monoid or a monoidal category, and eventually we'll assume it's symmetric and even more, then you can construct a new category, which is called S inverse S. And the idea is that when you had this mimics in some way the way you constructed, if you have M a monoid, then you took M inverse M, right? So you took the group completion or the Grothendieck group of this monoid. So this is supposed to generalize that to the case of monoidal categories. Okay, so let's go through the definitions. So the objects of S inverse M, S inverse S are just pairs. So they are pairs M comma N, where M and N are objects of S. Okay. So the morphisms of S inverse S are really what are complicated. So what are those? So if you have objects M1, M2 and N1, N2 in the objects of S inverse S, so you look at collections of pairs of this form. Okay, this is some rather nasty looking thing. So you have S. So what is this S? So S is an object in your category. What are F1 and F2? F1 and F2 are maps. From where to where? So morphisms. From where to where? F1 is a morphism from S tensor M1 to N1. F2 is a morphism from S tensor M2 to N2. And now if you have two such pairs, we want to define an equivalence relation in them. So this is again on the lines of, you had equivalence relations that you had on M inverse M. So this is similar to that. I mean, equivalence relations that gave you M inverse M. So remember, M inverse M was what? It was M cross M, but then you had some, M minus 0, and then you had some equivalence relation on that. So here you have something similar. Okay, so you have two pairs like this, S comma M1, S comma F1, F2, and S prime comma F1 prime, F2 prime. So these are said to be equivalent if there is a tau, which is an isomorphism from S to S prime. And what does that isomorphism do? Well, it makes this diagram commute. So let's look at this diagram. Aha. And I have so there's a typo here, right? Yeah, okay. So I think yeah, my bad. This is a mistake. Yeah, sorry. So this is not correct. So both of them are NI. Yeah. So you have S cross S tensor MI to NI. I'm doing for 1 and 2 simultaneously. S tensor MI to NI. You have a map Fi. S prime tensor MI to Ni. You have a map Fi prime. And then this tau gives you tau tensor Mi, which is from S tensor Mi to S prime tensor Mi. And then here you have equality. And then this diagram should come. Okay, so Fi prime composed tau tensor Mi should be equal to F. That's the definition. And this should happen for both I's 1 and 2. Okay. And then what are the morphisms between M1, M2 and N1, N2? They are equivalence classes of collections of pairs as above. Okay. So what you should keep in mind is that it's an equivalence class of pairs. And what kind of pairs? This kind of pairs. S comma F1 comma F2. Okay. So it starts with an object. Then there is a map from that object tensor with the first object to the first object. And then there is a map from that object to tensor the second object to the second object. Okay, this is what you should keep in mind. Okay, so now let's look at how we can think of S being quotes inside S inverses. So there is a functor from S to S inverse. I mean, there are plenty of functors, but there is one functor like this, which is obtained by M goes to 1 comma M. And if you have excuse me, a morphism from M to N, excuse me, I need to drink some. Yeah, excuse me. Yeah, if you have a morphism from M to N, so M and N are both objects of S, and you have a morphism there. So now I need to define a morphism from 1 comma M to 1 comma N. How do I do that? Well, an object, remember, is given by equivalence classes of pairs. So I look at the equivalence class corresponding to this pair. What is the pair? So first I need an object. So I'll just take the object 1. Next I need maps. So maps from where to where? Let's write that down. So once I have 1, I need a map from 1 tensor 1 to 1. And I need another map from 1 tensor M to N. These are the two maps I need. Okay. So what is the map I take for this? This is the map row 1. This is the map row 1. And what is the map from 1 tensor M to N? Well, we have already seen that 1 tensor M is really the same as M. You can drop that 1 tensor. You can do that using this. Oh, I've used. Okay, I should use lambda M. My bad. Yeah. So So the way we were dropping one tensor was via the uniters. So one tensor M to M, there was a isomorphism given by lambda M. So first you do one tensor M to M, and then you have M to N is already given F. So you have the composition F compose lambda. That's this map. So you have the equivalence class of that. And then of course one has to check that this indeed gives you a functor. So compositions, identities, etc., etc. Okay, so that part I'm kind of skipping. And now you can so note that on the left hand side S, you have a monoid functor tensor, and you can extend that sort of preserving this functor that we have defined. So I want to extend this tensor to S inverse S, but sort of in such a way that it respects this functor. Okay, so the monoid functor tensor on S is extended by the functor M comma N. So what do I mean by extended? So what I mean by extended here is I had a map. So I have a map S cross S to S, and now I want to get a map S cross S inverse S to S inverse S. Okay, so what you should think of here is as if this category S is acting on this other category S inverse S. In fact, there is a definition of such things, and that's used in what's happening next. But okay, we'll see how far we can go. Okay, so I want to give a map S cross S inverse S to S inverse S. Okay, so what I'm saying is I know here I have just the tensor. So here I want to extend this. Okay, so how do I extend this? So if you take S comma M comma N, the pair M comma N, I send it to M comma S tensor N. That's this map. Okay, and this extends your original definition, because if you have just a single object N, so N went to 1 comma N. So when you have S tensor 1 comma N, that goes to 1 comma S tensor N, which is the image of S tensor N. So this extends the tensor, but in the sense that it's an action now. Okay. Okay, and I also need to do that for morphisms. So I've written down how to do that. Namely, if you have a pair T comma F1 comma F2 like this, then you send it to the pair T comma F1 comma, you take the tensor only on the last part, right? Because you are not really changing anything on the first part. Okay, so you take it to the last part. Sorry, what happened? So you have S tensor F2. Okay, now it's again a check that this is well defined and so on. So because remember, this was an equivalence relation, so one has to check this. Now this is where you need that it's symmetric, and I'll kind of indicate why. So remember that what should this S tensor F2 do? So it should take T. It should take T tensor S tensor M2 to S tensor N2. That's the definition. That's what this should do. But now I can say this is isomorphic to T tensor S tensor M2. But I really need to interchange that S and T. Okay. So I want some way of saying that this is isomorphic to S tensor T tensor M2. And then you're in business, because this is isomorphic to S tensor T tensor M2. And that has this natural map S tensor F2. Okay. So in order to do this, I have this part here. where I need to flip S and T. So here I need that tensor is symmetric. Okay. So from this point on, for this purpose, in order for this to work, we need that our category is symmetric monoidal. Okay. So the definition of S inverse S, you don't need it, but really to use it in any meaningful way, you have to assume it's symmetric monoidal. Okay. And this is, yeah, I think, okay, 425. Okay, let's run now. So now you have somehow embedded S inside. Well, not embedded, but you can think of S to S inverse S, right? So um, um, the okay, the point is, I mean, what is this new space S inverse S? What is it achieve? What are you trying to achieve? So remember, when you had monoids, you were trying to achieve that if you take anything sort of non-zero, you wanted to create an inverse for that, right? You wanted to create an inverse for that. So that means in some way you wanted to say that when you take addition by S or whatever, multiplication tensor with S, that map gives you an isomorphism, right? Because it has an inverse, because S has an inverse. So here, this is like the map. If you think of it, this thing here is that version of the map tensoring by S. This is the action of an element S on S inverse S. And if S inverse S is the correct construction, then this action should be invertible in some sense. So this should be in some sense invertible. And this is really the punchline. It's not invertible in the categorical sense, but what we can do is we will associate to it, we will produce another functor S inverse S to S inverse S, which is like its inverse. And inverse in what sense? So let me give names. So if this functor here is called F and this functor here is called G, then what we can say is that F compose G, this is the functor S inverse S to S. Well, what we can say is that there is a natural transformation this way. And we can also say there is a natural transformation the other way. Okay, so once you have natural transformations like this, it tells you that when you go to the classifying spaces, so if you take B S inverse S to B S inverse S, BF and BG, so the composition is homotopic to the identity both ways, right? So that means BF and BG are homotopy equivalences. Okay, so what have we done? This S action that we had here, this F was like the S action. And what we have done is that, well, we don't know how to invert it in the sense of category theory, but when you go to the corresponding topological space, the classifying space, at that level, the map that it produces is a homotopy equivalent. So you can invert it, right? Because it's a homotopy equivalence, right? The inversion in the sense of homotopy equivalences. So that means there is BG. So that's really the in what sense this is this is a generalization of the what happens for monoids. Okay. So I see I haven't even been able to define the K groups. So I'll leave it to you to read G so that I can at least. Actually, G is very easy. For F, you took tensor on the right term. For G, you take tensor on the left term. That's why you had sort of two terms, right? This is also how you do it for in the usual monoid situation where you have M cross M, and then you sort of play around with the two. Okay, so I think since it's 4:30, let me end with this definition. So if you have a symmetric monoidal category in which every morphism is an isomorphism, so I'll explain next time maybe why you need this, but hang on for now. That suppose you have this condition, then you define Kn of S to be the nth homotopy group of the classifying space of S inverses. Okay. So this is the definition of K theory for symmetric monoidal categories with this extra property. Okay. Without this property, this definition is not really very meaningful, and I'll try to sort of say why next time. Maybe one last comment is that if you okay, I'll explain this later because this needs to be explained. Yeah, maybe Dipankar, maybe I'll stop here since it's 4:30. Is that okay?
All right, no problem.
Because I mean,
if,
otherwise, this is going to
if
take.
if you have any ending line, you can just say that maybe for today's lecture because we started late anyway.
Okay, fine. Then I can continue for a couple, but I can't like I definitely can't go to the next part. But maybe what I'll say here is I'll just mention these two things, namely, let's look at what is pi naught of a category. So if it's a symmetric monoidal category, so if it's a symmetric monoidal category, then what is pi naught? So okay, I should be careful here. I mean, this is one reason why we have this assumption. So suppose you have a symmetric monoidal category in which every morphism is an isomorphism. Okay. So then if you take pi naught of S, then that is really the abelian monoid with elements which are isomorphism classes of S, right? So so all the isomorphism classes, each isomorphism class gives you one element, because those are the only morphisms in this category. That's what we assumed, right? And remember that in constructing pi naught, you have to take what you have to look at. You have to look at connected components. So so when I say pi naught S, of course I mean pi naught of B of S, right? So you have to look at pi naught of BS, which means the connected components. And what are the connected components? Those are given by whenever there are morphisms between objects, right? Then they'll be in the same component, right? And what are the morphisms here? They are only isomorphisms. So this will give you only isomorphism classes. Okay. So pi naught S is the abelian monoid with elements which are isomorphism classes of S. And I'm saying abelian monoid, so I should specify what is the operation. The operation here is that operation on S. Yeah, that gives you an operation on these on pi naught of S. Okay. So now if you take K naught of S as we have defined above, then that's pi naught of S inverses, which means pi naught of B of S inverses. So this is the group completion of the monoid pi naught S. Yeah, so this is the same theorem that we had when Professor Amit Kuber started from. Okay, and what is the idea here? The idea here is, I can just very briefly, I'll sketch out what is happening here. So if you have M1 comma M2, to n1 comma n2. So let's look at morphisms, right? In S inverse S. So morphism is given. Oh, sorry. Apologies. Yeah. So I have m1 comma m2 to n1 comma n2, and I have a morphism like this f comma. Oh my god. My bad. S comma f1 comma f2. This is how a morphism look, meaning up to equivalence. Okay. So now remember, in this category you have only isomorphisms. What is the data given? S is an object of capital S, and f1 is S tensor m1 to n1 f1, and S tensor n2 m2 to n2. This is the data of the morphism. Okay, so now let's understand what this means. The only morphisms here are isomorphisms. So this better be an isomorphism, and this better be an isomorphism. Okay, so essentially, and because it's an isomorphism, now you can sort of remember this is everything is up to equivalence. So you can really replace this, and you can say that the only morphisms in this in this category S inverse S are going to be of the form up to isomorphism. Up to isomorphism, they will be of this form. They'll always be of this form, where it is S comma identity comma identity. Okay. But what is this really saying? It's saying, well, when are two things going to be the same? Suppose I want to ask, when are these two things going, when will these two things be in the same component? Well, they'll be in the same component if after some, after taking some some morphisms like this, this is equal or isomorphic. Which again, when you say isomorphic, what does that mean? It will force that S tensor M1 is S prime tensor N1 and S tensor M2 is up to isomorphism S prime tensor N2. Which is exactly the same kind of relation that you had, if you remember, in when you converted, when you took the Grothendieck group. Yeah, and this is sort of the hand waving proof of why this becomes the Grothendieck group. Okay, so we have recovered K naught from this construction, and what we'll see at least in the special case where it's only isomorphisms, and I think we'll continue next time and see for the higher K's what happens. Maybe this is a good place to stop.
All right. So this was really a beautiful lecture. Thanks, Professor.
Thank you.
We can continue from here next time.
Yeah.
All right. Thank you all for being here. See you next week.
Yeah. See you. Bye.
Please share the notes.
Yeah, sure. If there are any questions, go ahead.
Yeah, sure. Yeah, I forgot.
Yeah. Oh, I see that pi1 has got erased.